In this video, I'll solve few problems of linear algebra. See the first problem, find a linear transformation t from r square to r square such that t of 1, comma 0 equal to 1, comma 2 and t of 0, comma 1 equal to 4, comma 3. So finding a linear transformation means where t of x, comma y goes to. That we have to find out in terms of coordinates. X, comma y is the general coordinate of r square. We know that the standard basis of R square is 1, 0 and 0, 1. These two vectors form standard basis of R square. So any vector in R square is written as x comma y that can be written in terms of a linear combination of standard basis. That is x into 1 comma 0 plus y into 0 comma 1. You will get this back. Now apply linear transformation on both sides. T of x comma y is T of this value. As it is a linear transformation says that alpha v plus beta w, if t is linear, alpha into t of v plus beta into t of w. So same rule applies here because t is a linear transformation already given. So x is a coefficient outside t of 1 comma 0 plus y into t of 0 comma 1. But they had already given t of 1 comma 0 is equal to 1 comma 2. Substitute plus y into 0 comma 1 goes to 4 comma 3. Now x into 1 comma 2 is nothing but x comma 2x. So x plus 4y comma 2x plus 3y. Adding the corresponding components, you will get the required linear transformation. Now the second problem, let t from r cube to r cube be defined by t of x comma y comma z equal to, this is the linear transformation given. You have to show that t is non-singular. So you should know what is meaning of non-singular transformation. The given transformation is non-singular if t of v equal to 0 implies v equal to 0. That means only the 0 element is mapped to 0. Other than 0 element, there is no other element or vector which is mapped to 0. So therefore in this case t of x comma y comma z equal to 0 means you have to prove that x, y, z all three values are equal to 0. So now let us substitute the value of t of x comma y comma z that is given here. So substitute this, that becomes equal to 0. So when you equate them, you will get individual equations equal to 0. So now this is a homogeneous system of linear equations. Therefore, to solve homogeneous system of linear equations, we have to find out the rank of the matrix A. So that is rank of A is found using the coefficient matrix. First write the coefficient matrix 1, 1, minus 2, coefficients of first equation. Then second row 1, 2, 1. Third row 2, 2, minus 3. Okay. Now you have to uh, reduce it to row echelon form or just row echelon form to find its rank. And we know that if rank of A equal to number of variables, then there does not exist any non-trivial solution. If rank of A is less than number of variables, then there exists non-trivial solution. Non-trivial solution means the solution other than zero solution. So here no non-trivial solution. Here non-trivial solution. So in this case no non-trivial solution. Only zero solution in this case. If it is less than number of variables, then there exists a solution other than zero solution. So here I have to reduce it to the row echelon form. Now first number non-zero element of first row is 1. Now elements below the zero elements must be made 0. So here this must be made 0. This is also to be made 0. So I have to apply the operation. R2 changes to R2 minus R1 and R3 changes to R3 minus 2 into R1. So first row as it is, second row 1 minus 1 0, 2 minus 1 1, 1 minus of minus 2, that is 1 plus 2 is 3. Then 2 minus 2 0, 2 minus 2 0, then minus 3 minus 2 into minus 2, that is minus 3 plus 4, which is nothing but 1. So now it is already in the row echelon form, reduced row echelon form itself. Because the first non-zero entry of second row is 1, element below which is already 0. No need to make anything 0 now. It is in the reduced row echelon form. Therefore, rank of A equal to number of variables now. Rank of A is number of non-zero rows. There are 3 non-zero rows which is equal to 3, which is same as number of variables 1, 2, 3, x, y, z, 3 variables. If rank of A equal to number of variables, then there exists only zero solution, no non-trivial solution. Therefore, the values of x, y, z must always be equal to 0. Hence, you will get t of x, comma y, comma z equal to 0, 0, 0 implies x, y, z equal to 0, 0, 0. That means only 0 vector is mapped to the 0. Hence, T is a non-singular transformation. Here, this can be reduced row echelon form or row echelon form, but to find the rank, row echelon form is also fine or reduced row echelon form is also fine. So in this case now we got row echelon form because the elements above I have not made 0. So that is fine, just you have to get either row echelon form or reduced row echelon form to get the rank of the matrix. Now one more question. Define a vector space over a field. So the definition goes like this. Let V be a non-empty set and F be a field. And the two binary operation, this is plus, which is called as vector addition, and dot, scalar multiplication. They are defined by vector addition is a mapping from V cross V to V in such a way that V comma W, this is V comma W goes to V plus W, and scalar multiplication is a mapping from F cross V to V, where alpha comma V goes to alpha dot V. I have taken here alpha, beta, gamma as scalars and V, W are vectors. In some textbooks, they may take alpha, beta as vectors and A, comma B as scalars. Anything is fine, but you have to mention which is a scalar and which is vector. Now, V under addition and scalar multiplication is vector space if it satisfies the following axioms. That first one is V under vector addition is an abelian group. So, elaboration written here. What is an abelian group? Abelian group with respect to addition. Therefore, it should satisfy closure law with respect to addition. V plus W belongs to V for all V comma W belongs to V, and associative law V plus W plus U is V plus W plus U for all U V W belongs to V. Then existence of identity. 0 is the identity element with respect to vector addition. Existence of additive inverse. Minus V is the additive inverse with respect to the given vector V. Next, V plus W equal to W plus V, that is commutative law, because it should be an abelian group for all V comma W belongs to V. And the second condition is the scalar multiplication should satisfy these. Scalar multiplication is distributive, that is alpha into V plus W equal to alpha V plus alpha W. This scalar multiplication distributive over vector addition. Similarly, vector scalar addition is distributive over vector the scalar multiplication. Alpha plus beta dot V equal to alpha V plus beta V. Then associative property, alpha beta into V equal to alpha into beta V, and action of 1 into V equal to V. If you have to mention this for all V comma W belongs to V and alpha comma beta belongs to F. If it satisfies all these conditions, we call V as a vector space over the given field F. Now, next question is, find the dimension and basis of the subspace spanned by the vectors 2, 4, 2, 1, minus 1, 0, 1, 2, 1, and 0, 3, 1 in V3 of R. V3 of R is nothing but R cube. R cube over the field of reals. So what you should do first is the given vectors, you have to write them as rows of a matrix. So form a matrix by writing the given vector as its rows. So first vector 2, 4, 2, second vector 1, minus 1, 0, third vector 1, 2, 1, fourth vector 0, 3, 1. Now you have to reduce it to the row echelon form. So for the first non-zero entry of the first row should be equal to 1, reduced row echelon form. So I will divide the first row by 2. 2 by 2 is 1, 4 by 2 is 2, 2 by 2 is 1. Rest all rows as it is. Next, below the first non-zero entry of a first row, all entries must be 0. This is 0, but these two are not 0. Therefore, you have to apply the elementary operation. R2 changes to R2 minus R1. So in that case, 1 minus 1 becomes 0. R3 changes to R3 minus R1. So first row as it is, last row as it is. That these two rows will change. 1 minus 1, 0, minus 1 minus 2 minus 3, 0 minus 1 minus 1 minus 1, 0, 2 minus 2, 0, 1 minus 1, 0. Now again, there is a 0 row in between. So what I will do is I will interchange third row and the fourth row. So R3 interchanged with R4. 1, 2, 1, 0 minus 3 minus 1. So this comes down. This goes up. 0, 3, 1. Next, the first non-zero entry of the second row is minus 3. The elements below them must be 0. So here 1, 2, 1, 0 minus 3 minus 1, no change in first and second row. Third row I will change it as R3 changes to R3 plus R2. So 3 minus 3, 0, 1 minus 1, 0. So these two rows will become 0. You have to count number of non-zero rows. There are two non-zero rows. Hence, rank of the given matrix is 2. That gives you the dimension of the subspace spanned by the four vectors is same as rank of the given matrix. So we want to find out dimension of the subspace spanned by these vectors, which is same as rank of the matrix. Rank of the matrix is given by counting number of non-zero rows. There are 2, hence dimension of subspace spanned by these four vectors is also 2. Now you have to find out a basis also for that subspace. The basis is given by the linearly independent rows. See, first row and second row are non-zero. Therefore, the entries in the first row and the second row, these two vectors will form as a basis. So you can write 1, 2, 1, 0 minus 3 minus 1. So that is one set of bases, or else the first two rows are non-zero. Therefore, the first two vectors in the given set 2, 4, 2 and 1 minus 1, 0, because those two are the vectors in the first two rows. They are linearly independent. The vectors corresponding to the first two rows are linearly independent. Hence, they can also form a basis. Either this or this. Anything is fine. So, the first two vectors 2, 4, 2, 1 minus 1, 0. That set is also a basis of the vector space. Now one more problem. Find a linear transformation of t from r cube to r cube such that t of 1, 0, 0 equal to 4, 5, 8. T of 1 minus 1, 0 is 8, 10, 8. T of 0, 1, 1 is minus 3, minus 4, minus 7. Here they had given where the vectors are mapped to under this linear transformation. You have to find out the linear transformation where t of x comma y comma z goes to, that you have to find. So first you have to see whether these vectors are they bases 1 0 0, 1 minus 1 0 and 0 1 1. How to check whether the three vectors in R cube a basis or not? You have to find out the determinant formed by the those vectors as a rows of the matrix. Now find out the value of determinant. 1 into minus 1, rest all it is 0. So which is equal to minus 1, not equal to 0. So these three vectors are linearly independent. So if the three vectors are linearly independent in R cube, then that forms a basis. Therefore, 1 0 0, 1 minus 1 0, 0 1 1, these three vectors is a basis of R cube. Therefore, any vector of R cube x comma y comma z is a linear combination of the basis elements. So I don't know for what scalar it is equal to x. So I'll take a into 1 0 0 plus b into 1 minus 1 0 plus c into 0 1 1. So when you expand this like a plus b equal to x, then a 0 minus b plus c equal to the second coordinate y. Similarly, c equal to z because these two are 0. So I want the values of a, b, c, these scalars. So a plus b equal to x minus b plus c equal to y, c equal to z given. So add these two equations, minus b plus b cancels, a plus c equal to x plus y. But c is z, substitute here, a equal to x plus y, c comes to the other side, minus z. So got the value of A, C already got. Then B equal to, from this equation, B equal to x minus A. So B equal to x minus, what is the value of A? X plus y minus z. So x minus x cancels, minus y, minus of minus, plus z. So we got all the values A, B, C. But we want t of x comma y comma z, where it goes to. So apply t on both sides. So you will get t of x comma y comma z, as it is a linear transformation, t of a v is nothing but a into t of a. So a into t of 1 0 0 plus b into t of 1 minus 1 0 plus c into t of 0 1 1. We know where 1 0 0 goes to, that is given here. So it goes to 4 5 8, substitute, b is 8 10 8, says into minus 3 minus 4 minus 7. So this becomes 4a plus 8b minus 3c, then 5a plus 10b minus 4c, then 8a plus 8b minus 7c. Substitute the values of a, b, c respectively. A is x plus y minus z, b is minus y plus z, c is z. Substitute here one by one. Then simplify like this. 4x as it is there, because there is no other x term. 4y minus 8y minus 4y. Then minus 4z minus 3z minus 4z plus 8z, that gives you 4z. 4z minus 3z gives you z. Similarly here, 5x as it is, because there is no x term. Then 5y minus 10y minus 5y. Then minus 5z plus 10z, that is 5z. 5z minus 4z is z. Similarly do it for the third one. So you will get the required linear transformation. Now find the range space, null space, rank nullity, and hence verify rank nullity theorem for this linear transformation defined by t of x comma y equal to x plus y comma x. So we know the standard basis of V2 of R is 1001. So let us find out the matrix of linear transformation. T of 10 goes to 1 comma 1, because x is 1, y is 0, 1, 1. 0 comma 1 goes to 1 comma 0. So matrix of T is given by writing this as a column 1 1 1 0. Column wise we have to write. This is the matrix of T. Matrix of T and rank of the matrix of T and the rank of T will be same. So what we will do is, I will find out the rank of the matrix A. So 1 1 1 0, the first non-zero entry of first row is 1, below which it should be 0. You have to make it 0 by applying the operation R2 minus R1. So 1 1, 1 minus 1 0, 0 minus 1 minus 1. Okay. Now this is in the row echelon form. Rank of A equal to number of non-zero rows 2. So that is same as rank of the linear transformation. Rank is nothing but dimension of range space of T. So dimension of range space of T equal to 2. So I got rank of A or rank of T. This part is done. Rank is done. Rank of the linear transformation is 2. Now I am to find out range space. Range space of T is nothing but R of T. That gives you all those T of x comma y images where the transformation takes the given vector 2. If you collect all those vectors T of x comma y, you will get the range space. But T of x comma y goes to x plus y comma x, such that x comma y belongs to R. So this is actually the range space, but the dimension of the range space we got it as 2, okay, which is same as dimension of R square. Therefore range space of the linear transformation is nothing but the entire plane R square. That is because we got dimension of range space of T as R square, as 2. Hence it should be equal to the plane R square. Now to get the null space of T, you have to collect all those vectors which will map to 0. T of x comma y equal to 0. So this gives you x plus y comma x equal to 0 comma 0. So which implies x plus y equal to 0 and x equal to 0. So if you substitute here x equal to 0, y also comes out to be 0. Therefore, T of x comma y equal to 0 comma 0 only when x and y both are 0. Therefore, only 0 vector maps to 0. Hence, null space of T contains only a 0 vector. If any space contains only 0 vector, its dimension is always taken 0. So, dimension of null space of T equal to 0, nullity of T equal to 0. So, we got rank of T equal to 2 and nullity of T equal to 0. Hence, rank of T plus nullity of TU, add both 2 plus 0, which gives you 2. 2 is nothing but dimension of V2 of R. V2 of R is nothing but R square over the field of reals. This is how we can verify rank nullity theorem. Now one more, show that the intersection of any two subspaces of a vector space V of f is also a vector subspace, but is the union also a subspace? Justify your answer. So what I will do is, I will take two subspaces of V of f. So we know that to prove any set as subspace, alpha v plus beta w should belong to the given subspace whenever v comma w belongs to w and alpha comma beta belongs to w f field. Now we have to show that w1 intersection w2 is a subspace of v of f. So to do that, consider one element from W1 intersection W2. So consider V comma W belongs to W1 intersection W2 and alpha comma beta belongs to here. We have to prove that alpha V plus beta W belongs to W1 intersection W2. So as these two elements are in intersection, V comma W should be in both W1 and W2. Then only they will come under intersection. So V comma W belongs to W1 and V comma W belongs to W2. As W1 and W2 are subspaces, whenever V comma W belongs to W1 and alpha comma beta belongs to F, alpha V plus beta W should belong to W1. Similarly, alpha V plus beta W should belong to W2 because they are the subspaces already given. If this vector is there in both W1 and W2, it should come under W1 intersection W2. Hence, we got the required thing. Uh, Similarly, you can prove here that 0 is also in W1 intersection W2 because any subspace should contain the 0 vector. So here W1 and W2 are subspaces. Therefore, 0 should belong to W1 and 0 should belong to W2 also because they are subspaces. If 0 is in both W1 and W2, that should be in the intersection. Hence, we got all these three conditions. 0 belongs to W1 intersection W2. It is closed with respect to addition and closed with respect to scalar multiplication. Hence, W1 intersection W2 is also a subspace of V of A. Now, union of two subspaces need not be a subspace. One example is, take one x-axis. W1 is x comma 0 comma 0. Take y-axis, that is 0 comma y comma 0. Now take one vector from W1 1 0 0, another vector from the W2, that is 0 minus 1 0. Any vectors you can take. Now when you add these two vectors, you will get 1 minus 1 0. But that is not there in W1 union W2 because this is neither on x-axis nor on y-axis. It is in somewhere in xy plane. That won't come in union of these two x and y axis. Hence, W1 union W2 need not be a subspace of the given vector space.